Okay, so having an infinite number of answers can be problematic. Let's just go with that. So because more than one value of theta produces the same output value for trig functions, it's necessary to restrict the domain of each trig function in order to define the inverse trig functions. So we're going to use, instead of like capital sign or inverse sine and regular sine, we're going to start adding capital letters. So we're going to use capital S for sine, capital C for cosine, capital T for tangent. And when we're talking about the capital letter versions, we're talking about in a specific restricted domain. So for example, if we're talking about the capital sine of theta, we are talking about the normal sine of theta. The values that we get are still going to be found in the sine of theta. However, we're only talking about between, in radians, negative pi over 2 and pi over 2. Really what that means is we're talking about quadrants 1 and 4. Now, why those two quadrants? The reason for those two quadrants is the sine of an angle in quadrant 1 is positive. Remember, the sines are the y values. In quadrant 4, the sine is negative. It wouldn't make much sense for us to look for the sines in quadrants 1 and 2 because all the sines in quadrants 1 and 2 are positive. 1 and 3 could also work, but that'd be kind of weird. Like, honestly, I think that's the main reason. It's just because, like, why would we do that over here? Like, you're right. That is, I mean, I don't know if you were thinking it, but I was thinking it. That's negative. Why not use it? And we're going to try to keep just the attached ones. Now, for the cosine, we're going to be working with quadrants 1 and 2. So between 0 and pi. Because, again, similar to what we had in for sines, in quadrant 1, the cosine's positive. In quadrant 2, the cosines are negative. So we're going to get one possible answer for all the negative cosines, one possible answer for all the positive cosines. For tangent, we're going to go back to quadrants 1 and 4 because the tangent, remember, we can find that by doing the y value divided by the x value, is positive in quadrant 1 because it's a positive y divided by a positive x. Quadrant 4, the y is negative, x is positive, so in quadrant 4, the tangent of theta is negative. Let's take a look at some examples, or actually scratch that, I'm jumping ahead of myself. I'm just going to kind of reiterate this in the next page just a little bit. So here's a lot of words. So these functions can be used to define inverse trig functions. For each value of a in the domain of the inverse trig function, there's only one output value of theta. Therefore, even though the inverse tangent with a lowercase t of theta has many values, the capital inverse tangent, capital T, only has one value. So the inverse sine function, sine of angle, or inverse sine of a, my apologies, equals theta, because sine of theta equals a. There's only going to be one possible answer. The answers are going to be in quadrants 1 and 4. So we're going to talk about between negative pi over 2, and you'll notice I keep saying negative pi over 2, not 3 pi over 2. We'll talk more about that in a second. Or we haven't talked about it in degrees yet. We're going to go from negative 90 to positive 90. For cosines, it's going to be quadrants 1 and 2, so between 0 and pi, and 0 and 180. For the inverse tangents with the capital T, we're going to go back to quadrants 1 and 4 between negative pi over 2 and pi over 2, and between negative 90 and positive 90 degrees. Let's take a look at an example. So the first one, we're asked to evaluate each trig function, give our answer in both radians and degrees. So we're asked to find the inverse cosine of negative square root of 3 over 2. Now we're going to be looking in quadrants 1 and quadrant 2. Now again, going to the unit circle, we're going to look for what angle measure in quadrants 1 and 2 gives us the negative square root of 3 over 2 when we take the cosine of it. So let's go to the unit circle. So we're looking in quadrants 1 and 2, just the top two quadrants here. Let me erase some of these stray marks that I have left over. So in quadrants 1 and 2, we're looking for where cosine is equal to negative square root of 3 over 2. Looking over here in quadrant 2, we found a cosine equal to negative square root of 3 over 2. So in radians, we got 5 pi over 6 and 150. So our two answers, we're going to say theta equals 5 pi over 6 equals 150 degrees. I'd like you to pause the video and try the second one out on your own. The inverse sine of square root of 3 over 2. I want you to take a moment, think about what quadrants you're supposed to be looking in for the inverse sine, and then go look at the unit circle and figure it out. Okay, you paused it. You're back. Cool. So in the inverse sine with a capital S, we're looking in quadrants 1 and 4. You're always going to use quadrant 1. The only thing that changes is either quadrant 2 for cosines or quadrant, quadrant 4 for inverse sines and inverse tangents. So we're looking in quadrants 1 and 4 for where the sine is equal to, again, where is the sine of some angle equal to the square root of 3 over 2? So go into the unit circle, staring real hard at the right side of this graph. Let me erase those stray marks over here, not to distract. Looking real hard at the right side of this graph. Where is the sine equal to the square root of 3 over 2? There's only one spot on the right side of the graph. That's over here at pi over 3 or 60 degrees. So we're going to say theta equals pi over 3 or 60 degrees. All right. Let's keep this going. We're going to change it up a little bit. And we're going to say a painter needs to lean a 30-foot ladder against a wall. This seems unrelated. Whatever, we'll figure it out. Safety guidelines recommend that the distance between the base of the ladder and the wall should be 1/4 the length of the ladder. To the nearest degree, what acute angle should the ladder take with the ground? Let's start drawing a picture here. Let's draw some sort of right angle, or right triangle. I don't care which direction it's facing. I'm just going to draw this one. Here it is. Now the ladder is 30 feet long. The only other thing we know is it says safety guidelines recommend that the distance between the base of the ladder and the wall should be 1/4 the length of the ladder. Now, in order for us to figure out 1/4 the length of the ladder, we're going to do 30 divided by 4. That's going to give us 7.5 feet. So this part of the wall, or this part from the ground, should be 7.5 feet. And we're trying to figure out what's the angle that's going to be made between the ladder and the ground. The acute angle, which means this one. Because technically there is another angle here. It's the supplementary angle to that angle we're trying to find. So in other words, it adds up to 180 with the angle we're finding. Don't worry about that. So we've got some angle measure. And we have this leg here, the short side, and the hypotenuse, the long leg. This is the adjacent side, and this is the hypotenuse. Thinking about what trig function uses adjacent and hypotenuse, that's cosine. So I'm going to use capital cosine. It doesn't really make a difference in this case. But the capital cosine of some angle theta is equal to the adjacent side, 7.5, over hypotenuse, 30. Now, we can actually reduce this, just to be consistent with what I was saying earlier. Adding units, the units are going to cancel off. Now, 7.5 over 30, that's 1/4. Now, even if you don't see that right off the bat, well, the ratio, we know that 7.5 is 1/4 as long as 30 feet. So we got the cosine of some angle equals 1/4. To help us figure this out, because we don't have the cosine of some angle equal to 1/4 in the unit circle, this is where we're going to need to use the inverse trig functions. So we're going to say the inverse cosine of 1/4 equals whatever that angle measure theta is. Now, because it's not in a unit circle, I don't expect you to have all this stuff memorized. So what I'm going to do is I'm actually going to go to our calculators. And you can use pretty much any calculator that has sine, cosine, and tangent on it. I'm going to be using the TI-84. There we are. Let me clear out all this old info. So we know where sine, cosine, and tangent are. Sine there, cosine there, tangent there. You'll see above them in the slight left corner above those, we got sine inverse, inverse sine, inverse cosine, inverse tangent. We want to use inverse cosine here. So to get to those, I wish it was color coded on this screen, but it's not. That's okay. We'll do second, and then press the cosine button, and then it says inverse cosine. And then we're going to do 1 divided by 4. And I'm going to close my parentheses just to be consistent. And I'm going to hit enter, and it gives me 75.522, etc. Now, if you got something different, heck, even if you got the right answer, I do want you to check one thing. Let's go to the mode. And I want us to make sure we're in degree mode. Most of the time when we're talking about angle measures in real life context, we're talking about degrees. Radians come into play with arc length. That's important in some real life context. But for this context, we're going to be talking about it in degrees. In fact, this question asked for it in degrees. So make sure when you're doing problems like this, you go to mode. You make sure that the third option has degree selected. It's got the dark background and light letters. Mine already did. So let me show you what it would look like if you had it in radian mode. You would have accidentally got 1.3. That doesn't make much sense. 1.3 degrees, not very big. So we're looking for degree mode. So again, 75.5222222. What? That's not that many twos. I stopped paying attention because really it says to the nearest degree. So that means we're going to cut it off after this decimal point. So 75 point, and then we're done. Except we got to use that 5 and round up. So let's go back to the notes. Let's add that in. Get my mouse off the screen. So we're going to say theta equals, it was 75.5, so that means we're going to have to round it up to 76 degrees. I would like you to pause this video, take a few moments on the next example, see if you can set up the next example properly, and I'll rejoin you in a second. Okay, you're back, you paused, we're good. A group of hikers wants to walk from a lake to an unusual rock formation. The formation is 1 mile east and 0.75 miles north of the lake. To the nearest degree, in what direction should the hikers head from the lake to reach the rock formation? Now, I'm just going to go based off of what we usually do when we're drawing things in two-dimensional planes. If you're thinking about your cardinal directions, typically the top part of the paper is north, bottom part of the paper is south, right side of the paper is east, left side of the paper is west. That's just pretty typical. So we're going to have a starting point here. And that starting point is a lake. We're starting at the lake. So let me draw. I've been practicing my art in this time. This is a lake, of course. Now, we're told that from the lake to the formation, it says it's 1 mile east. So that means we're going to head 1 mile this way. Let me draw a straight line there. So that's 1 mile east. And then 0.75 miles north. Now, folks, this is not going to be to scale, and that's perfectly okay. The more important thing is that you label. Because if you label it, then those are the labels. Then they're the right dimensions. So the end there is our rock formation. Our rock formation, it's a very interesting rock formation. It's a lopsided smiley face. Just an interesting rock formation. So it's 1 mile east and 0.75 miles north. Now, typically we wouldn't go that unless, like, if there's some like treacherous thing in the middle here, we'd probably just avoid that. But if there's no such treacherous thing, we're probably just going to go the shortest path. Remember, the shortest path between 2 points, thinking back to geometry, is a straight line or a line segment. So we're asked to figure out really what this angle is here. So we have an angle measure, or we're looking for an angle measure. The side, this 0.75 here, if we finish off this right triangle here, this is the opposite side. And then this 1 mile would be the adjacent side. Thinking about what we know about sine, cosine, and tangent, we need to know one, or we need to use one that uses opposite and adjacent. So we're going to say the tangent of some angle equals the opposite side, 0.75 miles, to be clear, over the adjacent side, 1 mile. Now, I'm going to do some very fancy math here. Those units cancel out. 0.75 divided by 1, even I can do that in my head, that's 0.75. Now, we're trying to figure out that angle measure. That angle measure, theta, is going to be the inverse tangent of that 0.75. So we're going to go back to our calculators. Let me minimize this a second. Going back to our calculators, we'll do the inverse tangent. So we'll do second tangent, then 0.75 and then we'll close our parenthesis just to be consistent, hit enter, and we get an angle measure. Now, again, just double check your angles, making sure that you're in degree mode. Go to mode, still in degree mode, we're good to go. So we're going to say it's about, I think it asks us to round to the nearest degree. So 36.86, that's going to round up to 37 degrees. Let me bring up the notes again. There we go. So we're going to say theta equals 37 degrees. Now, typically when you're giving directions, especially using the cardinal directions north, south, east, and west, you want to give a little bit more than just that. So I'm going to say it's 30 degrees north of east. It's as if, what that means is if you're facing east and you turn 37 degrees, so if you're facing this way and you turn 37 degrees towards the north, you're going to be facing the right direction. Now, if you wanted to, you could describe this a different way, because every right triangle has a very similar right triangle that you can draw off of that. And by similar, I mean congruent. We could also draw a straight line tool. Could also draw a triangle that looks like that. That's not my best. Let's fix. No, that made it worse. This is entertaining, and I don't feel like redoing this video. Okay, we're going to call that good. So, the other way we could describe this is by describing this angle. Well, keep in mind that 37 degrees that we just found there, and whatever this angle measure is, have to add up to 90 degrees. They're forming a right angle. So it could also be theta equals, the other angle would be 53, in other words, 90 minus 37 degrees, and I'll just say east of north. There are probably more efficient ways of describing this, especially for those of you that are in aviation classes. Let me know. I'm more than willing to listen. We've got one last example. I think I'm just going to keep this video rolling. Yeah, we'll just keep this video rolling. This one, we're asked to solve each of these to the nearest tenth using the given restrictions. So now you'll notice these are very similar problems. It says, what's the sine of theta for 0.4 for negative 90 degrees less than or equal to theta less than or equal to 90 degrees. So we're looking in quadrants 1 and 4. So what I'm going to have us do is we're going to use the calculator again. Actually, before we use the calculator, I'm getting ahead of myself, sorry. Let's draw a quick sketch of what we're talking about here. So we're talking about between 90 degrees and, negative 90 degrees, so down here, and positive 90 degrees, up here. We're looking for an answer there. Now, since we know the output sine is positive, thinking about the x and y coordinates on the unit circle, the sine is the y coordinate. So in quadrants 1 and 4 there, I think I might have said 1 and 2 earlier, my apologies. In quadrants 1 and 4 there, the only place that has a positive y value is quadrant 1. So let's just draw some angle here. We don't know what that is yet. But again, we're choosing this part because the sine of some angle equals positive 0.4. Now we're going to use our calculators again using the inverse sine. So we have the inverse sine of 0.4. I missed the inverse there. Let's jump to our unit circle there for a second. Or not a unit circle, goodness, I'm tired. Calculator for a second. Let me just try this. It'll be a little quicker. So we'll do the inverse sine. I'm already in degree mode. I've checked like 1,000 times of 0.4. Close the parenthesis. And we get a value of, let's see, to the nearest, let's go to the nearest tenth, 23.6 degrees. Okay, not too bad. Let me go back to the notes. Sorry, my computer's being a little fussy. So we got 23.6 degrees. Okay. Those numbers look really bad. 23.6 degrees. Alright, not bad. The next one, it says find the sine of theta equals 0.4. Didn't we just do that? For 90 degrees less than theta less than 270 degrees. I swear we just did that. We did, except for the domain's different. We're talking about between 90 and 270 now. So let's draw a quick quick representation of where that's going to be. And the place that's going to be between 90 and 270, that's over here. Quadrants 2 and 3. We finally get to mention quadrant 3. We've avoided it so far in this in this section. Okay, so we're looking for the sine of some angle equals 0.4, 0.4. So again, the sine is positive. That means we're still talking about some angle up here. So we're actually mentioning quadrant 3 for once, but we're still not going to use it. Not in this example. But we're talking about an angle over here. Now, if you were to go through, do that whole process again, use the calculator to do sine of theta equals 0.4, or the inverse sine of 0.4 is, you're going to get 23.6 again. Your calculator is going to tell you the same answer. It's not going to give you a different answer because that'd be weird. It'd be broken. So what? So how do we do this? Well, let me draw you the other angle we just found. Maybe I can draw it decently well. This one that we just found was 23.6. Cool. We just found it. Here's another 23.6. We talked about reference angles a couple sections ago, and this is where they really come into play. So that is 23.6 degrees there. We're looking for the standard position angle. We're looking for from this positive x-axis over here, how big is that angle? Now, we know that if I were to go a little bit further, that'd be 180 degrees. But we're not going that far. We're actually going to go just a little bit less. We're going to say it's 180 degrees minus that reference angle, 23.6 degrees. And that's going to give us 156.4 degrees.